Today, we're going to be starting your Module 2, Topic 3, your gravimetric methods of analysis. So under this topic, we're going to be looking at different techniques through which you can determine the amount of your analyte or your unknown by utilizing the measurement of mass. Now, your gravimetric analysis, we're going to be looking at two types of gravimetric analysis. That is your precipitation and your volatilization. And we're going to be starting off with your precipitation. Under your precipitation, you are starting off by essentially drying and weighing the sample to be analyzed and dissolving that sample in a suitable solvent that is in excess. The reaction between your sample and your solvent is going to give you your precipitate. Alright, so hence the name, your precipitation gravimetric analysis. And this precipitate is going to contain the ion that you want to know the mass of. So an example of a precipitation is the percentage of chlorine in a sample of a copper chloride can be determined by dissolving a known mass of water, acidifying the solution with your nitric acid, and adding your silver nitrate to precipitate silver chloride. The silver chloride can then be isolated by filtration, dried, and weighed. And then from there, you can determine the percentage of chlorine in your sample. So your precipitate that you're forming from the reaction between your sample and your suitable solvent must be in as pure of a form as possible. It must be stable, meaning it doesn't break down or interact with the atmosphere. It must be highly insoluble in your selected solvent. All of the ions that you're trying to analyze remain a part of your precipitate. And the larger it is, the better it is in terms of the filtration process, so it doesn't slip through your filter paper or your vacuum filtration funnel. So in order to achieve that high purity of a precipitate and to limit co-precipitation, you're going to be carefully and slowly precipitating in terms of gravimetric analysis methods, and you're going to be washing thoroughly. Now we're going to look at some of the apparatus that are used in your precipitation gravimetric analysis. So in the first step here, it was weighing the sample to be analyzed. So of course, you're going to need your analytic balance. Alright, so this one is a very precise balance and it weighs up to 4 decimal places. In order to separate that precipitate from this solution here, you're going to be undergoing your filtration, and specifically we're looking at your vacuum filtration. So here we have your Buckner filter flask, which is one of the apparatus for your vacuum filtration. It looks similar to one of the conical flasks you would have used in a titration, except you have this little side arm here, and this is attached to a vacuum. So this is your vacuum filtration setup. So as you can see, that arm that is attached on your Buckner funnel is connected to a vacuum pump or even a water aspirator pump. So this pump is going to cause that liquid or that reaction mixture to be sucked down and drawn through the funnel, sucked down here and drawn through the funnel into the flask below. And right in here, you're going to have that solid precipitate. So right up top here, you have your Buckner funnel. So this is a closer image of your Buckner funnel. Right, as you can see, there are a couple of holes in here to allow your solvent, your solution mixture to be drawn through. Here you have your diagram of your gravimetric apparatus. You have your Buckner flask, your Buckner funnel, that rubber band there to keep a tight seal and to ensure that vacuum pump suction is going. You have that rubber tubing that your side arm is going to be attached to, and this is attached to your vacuum pump. In addition to your Buckner funnel, you also have your sintered glass crucibles. These can be used for your filtration and can be placed directly in the oven. So it's a porous disc, you can filter, dry and weigh directly, and it cannot withstand temperatures of greater than 200 degrees Celsius. Aside from your sintered glass crucible, you also have your silica crucible, and this is used solely for the heating step. Right, so you have your precipitate in, and this is your silica crucible. So your silica crucibles are inert They're made of silica, as the name suggests, and they can tolerate temperatures greater than 200 degrees Celsius. Alright, and they have a high resistance to heat shock. But unlike your sintered crucible, they cannot be used for the filtration step. So the procedure is to dry the sample in the crucible in your low temperature oven, cool the sample to room temperature in a desiccator, and then weigh, heat again, cool, weigh until the mass is constant. You're going to place your sample in a desiccator and you're going to close this desiccator. This desiccator prevents your sample from absorbing any extra moisture from the atmosphere because it's now in a sealed enclosure. In addition to this, your desiccator also contains desiccants, and these desiccants can be your silica gel that would then absorb any moisture that your precipitate has within this sealed enclosure. In addition to heating your precipitate on the open flame, it can also be heated in an oven or in a furnace. So after your precipitation, the amount of analytes in the original sample can be calculated from the mass of the precipitate and its chemical composition. First example states, the treatment of a 0.800 gram sample of impure potassium chloride with excess aqueous silver nitrate resulted in the precipitation of 1.460 grams of silver chloride. You're asked to calculate the percentage of potassium chloride in the sample. So because this sample is impure, you might have other contaminants present within the sample. The experiment decided just to isolate all of the chloride ion by precipitating your silver chloride. So from this question, you're giving the mass of your silver chloride. So with the mass and the molar mass of your silver chloride, you can then determine the number of moles of your silver chloride. So once you have the number of moles of your silver chloride, you can then determine the mole ratio by writing down a balanced equation showing the reaction between your potassium chloride and your silver nitrate. So from that equation, it's a 1-to-1 mole ratio. Once you have the number of moles there, you would then take your molar mass of your potassium chloride and determine the mass of your potassium chloride. So this was the yield of your potassium chloride over the mass of your impure sample. You can fill in the step 1 to 4 and we'll look at it in class. Next in class, we're going to look at a riddle me this to riddle me that. You can take a look at it right now. I looked in the mirror lately and I've been serving granular and stable. I lost all my water weight with the help of a little suction. No, not liposuction. Due to my weight loss, I can't keep myself warm, so I like to get toasty with my friend Silica, and on really chilly nights we have a staycation at the Desiccator Motel. So the next type of your gravimetric analysis we're going to be looking at is your volatilization, and this involves heating without the precipitation step occurring beforehand. And your volatilization involves heating an analyte or its decomposition products into the gaseous form. So it can be direct or indirect. So direct, you're going to be collecting and weighing that gaseous product. So the gas that is coming off, whether it's water vapor or carbon dioxide gas, that is a more common example of your direct methods. You would collect the gas and you would weigh it, or it can be done indirectly. So the mass can be determined indirectly from the loss in the mass of the sample. The loss of your water vapor can be determined by taking your initial mass and subtracting your final mass, and that change in mass equates to your water vapor. So some examples of your volatilization involves determining the amount of water of crystallization in a hydrated salt. So this is showing you the example of your water, the amount of water of crystallization in a hydrated salt. So here you have your hydrated copper 2 sulfate. This is typically your gravimetric analysis lab, and it is blue in color. You're going to be heating this sample to remove all of the water molecules that is present within this salt. So you're going to be heating it. Once it's cooled, you're going to wait, and you keep heating and weighing until you have a constant mass. So at the end, once all of your water is removed from your salts, you now have your white powder. And it can go back to blue if you wet it again. So here are some other examples of your hydrated salt. You can also collect your water through direct methods. So this is done by heating your sample and collecting the water vapor in a solid desiccant. So the amount of water can then be determined from the increase in the mass of the desiccant. Basically, a desiccant is going to be absorbing your water and absorbing your moisture. Common example of a desiccant is your silica gel, and this is just showing the color of your gel based on the amount of moisture that it is absorbing. Another direct method under your volatilization is your carbon dioxide gas in your carbonate containing materials. So you heat your sample with excess acid, and this is going to be evolving your CO2 gas. And this CO2 can be absorbed by either your soda lime or your ascarate. This is an image of your soda lime here. So just like your silica gel, the increase in mass of the soda lime is due to your carbon dioxide gas. And we just looked at your indirect method, which was your water of crystallization. This is a practice question. All right. So it says to measure the mass of a pure hydrate before heating. That was your 5.325 grams. Heat the sample to completely drive off all the water molecules in the crystal lattice. Measure the mass of the sample after heating, and this was after a few times of heating and weighing. So you obtain a constant mass of 2.601 grams, right? And this is your anhydrous magnesium sulfate. So you started off with a 5.325 grams of your hydrated salts, and after removing all our water vapor, we ended up with a 2.601 grams. So now we're going to be calculating the moles of your magnesium sulfate, and this is your anhydrous magnesium sulfate without the addition of with the loss of water. And I'm going to be dividing it by the molar mass of your magnesium sulfate. Around that. And in terms of your moles of water, you're going to have to start off with the mass of water. So you're going to be taking your hydrated salts. So the salt with your water was your 5.325, and then you're going to be subtracting your anhydrous salt. So the difference between these two salts is the loss of your water. So now in order for you to find the number of moles, you're going to be dividing it by the molar mass of water. So that's your 16 from your 1 oxygen, and your 2 hydrogens going to give you your 18 grams per mole. And I forgot the units on the other one, but you should get the gist from your unit one. So in terms of your moles of water, you should end up with... So now that you have your mole of water here, and you have your mole of your magnesium sulfate, you're then going to be dividing it by the smallest number of moles. So between these two values, your smallest number is going to be your 0.02161. So this divided by itself is going to give you 1 mole of your magnesium sulfate. And this divided by that is going to give you 6.9 rounded off to 7. So now you have 1 mole of this. So that means that if you were to write the formula for your magnesium sulfate hydrated salt, you're going to end up with your MgSO and your 7 H2O. Alright, so I give you 1 mole of the salt and 7 moles of the water. So this would be the practice question that we're gonna look at in class. And of course, we have another rhythmy that for this section. I've been raving to all my friends back home about my trip to Florida to make them all jealous. But honestly, karma has been beating me up. I underwent a color change from my blue cherry self to a dull off-white due to my dehydration and all this heat. The water loss also affected my weight. It kept on fluctuating until I was constantly skinnier and dried out. I need to jump up my crucible and back into some good water fun. Can you please tell me what's wrong with me before I fly back home? So this riddle me, that is taking place at a doctor's office. And you get to diagnose our lovely client. So to wrap up this topic, we're going to just be looking at your advantages and your disadvantages of your gravimetric analysis. Some of the advantages are that it is very precise and accurate analysis. You're using an analytical balance that goes up to 4 decimal places. You can identify your possible source of errors and you obtain direct measurements. It is cheap to carry out your experiments. And lastly, we have some disadvantage of your gravimetric analysis. It can be very time consuming, having to consistently heat and reweigh your sample. Only the analysis of a single element. Your methods for gravimetric analysis are often complex. The gravimetric analysis can be used to analyze and establish the purity of compounds used, has standards in other types of analysis, or for calibrating your instruments. Some examples of this are atomic absorption spectroscopy. It can be used to determine the concentration or the percentage of specific substances in mixtures and materials such as your soils, your drugs, your foodstuff. It can be used to maintain your quality control of your fertilizers, like the percentage of phosphate in your fertilizers. It can monitor the concentration of particles in the air, and it can be used for your combustion analysis. So this is going to be evolving your CO2 and your water vapor, so the masses of those can be determined.